Welcome to our 32nd Florence Bucke Prize Lecture. It's a real pleasure to have you all here this afternoon for us to acknowledge and recognize the contributions of one of our distinguished faculty members in science. So the Florence Bucke Prize, I will tell you, was made available through an endowment of the late Florence Bucke. She obtained a Bachelor of Arts at Western, and I guess must have been very passionately interested in science. So through discussions with the then Dean of Science, created an award which recognizes impact and contributions in the last 5 years. So this is a very special award. It's not a career award. It recognizes something that is relatively recent for a young investigator. So this, I would like to let you know our previous winners of the prize. So our current winner is Pauline Barmby, as you all know, from the Department of Physics and Astronomy. And we have had a long and distinguished list of winners in the past. I'll let you read the names here. Very prominent scientists in the faculty. And more recently, since I've been here, Brian Neff, our new, not so new, I guess, Associate Dean Research, John Corrigan last year, and a real pleasure to have here today Pauline Barmby and to recognize her contributions. I'm going to invite the Chair of Physics and Astronomy to talk a bit about Pauline Barmby and her contributions, and especially the recent innovations that have led to recognition for this award. Shantanu.
Thank you very much, Charmain, and welcome to the Department of Physics and Astronomy. We're, of course, very, very proud to be introducing our own Professor Pauline Barmby for this award. Let me give you a brief introduction, and you can yank me off if I go on too long. So I'd like to get across some of the reasons why we're very proud to have nominated Pauline and that she succeeded in obtaining this recognition. Pauline joined the department in 2007 as an assistant professor, and she was promoted to associate professor with tenure in July 2013. She obtained her PhD in astronomy from Harvard University in 2001. Where she worked under the supervision of the late John Huckra, who was an acknowledged extragalactic astronomy expert. Her thesis was titled Globular Clusters in the Andromeda Galaxy, something you'll see a fair bit of today as well. And the peer-reviewed papers that came out of that thesis demonstrated a lot of promise for her future career, something she has lived up to and taken to new heights. After obtaining her PhD, Pauline did not become a postdoctoral fellow. A little bit different path. That's, of course, the usual path for new graduates. She took on instead a research position of astrophysicist, that was the title, at the Smithsonian Astrophysical Observatory, or SAO, which is located at Harvard. She became a member of the Spitzer Space Telescope Iraq instrument team. I'm assured they were not spying on some Middle Eastern country. They were actually looking the other direction. And this mission, Spitzer, has provided a wealth of astronomical information at infrared wavelengths. Although Spitzer's main mission ended a few years ago, the data gathered with it has revolutionized our view of the cosmos and continues to help us gain new insights into several subfields of astronomy. While Pauline was at the SAO, she worked with one of the best groups of scientists in observational extragalactic astronomy, and she worked on the development of technology and instruments that consistently pushed forward our understanding of the field. Thus, Pauline acquired, even at a very early stage of her career, a level of experience and expertise that few scientists can hope to match over an entire career. And as I said before, that trajectory has just gone on and on. She has continued at a very high level. The 5 peer-reviewed papers from her PhD thesis alone have nearly 500 citations. However, if you look at the career, She's got over 9,000 citations now, from 99 peer-reviewed papers last time I checked. I'm sure it's 100.
I can't get that last one.
There's still something left to do. And with the 9,000 citations, that also translates to an H-index of 44, again, last time we checked. Okay, those are high numbers indeed. So we're very proud in the department to have Pauline as a colleague. She always makes herself available. She wasn't giving this talk, she'd still be here, I can assure you. She's available for departmental events. She can amaze us with her intense concentration, especially while walking the hallways of physics and astronomy. And her very colorful and witty aphorisms can leave the best of us perplexed and skeptical. Department people know that. Okay, so very much so, in addition to that, ultimately she's an exceptional scientist and a world-renowned leader in the field of extragalactic astronomy. Through her work, she consistently puts Western at the forefront of both the national and the international science community. And so with that, it is certainly my high pleasure to introduce Pauline to talk to you about the beautiful science of nearby galaxies.
Thank you very much, Shantanu, Dr. Dean. It's really wonderful to be here talking to all of you. And I guess I need to switch slides here, so let me just go ahead and do that. So what I hope to do today is to give you kind of an overview of what people who study nearby galaxies do, how we go about doing it, what we know and what we don't know, what we're trying to figure out in the field. And I'll try to do that by giving some quick snapshots of the kind of work that I do. And then give you what I hope is a very short view of what we think the future holds in this field. So I'd like to start off by insulting almost everyone in the room with this lovely quote from Ernest Rutherford. And what did he mean by that? Well, he's dead, we don't know. But you can argue that astronomy has a lot of stamp collecting aspects to it. You know, we go out and we find how many stars there are, and we look for all the galaxies, and we count them all up, and we give them funny names, and we put them in catalogs. What is that all about? Well, we do an observational science with very few exceptions. We can't have our stuff in a laboratory. We can't take it apart and see how it works. We can't put our galaxies in a different river and see if they swim better. That kind of stuff just doesn't work. So we're left with trying to make sense of what the universe gives us. And so the stamp collecting aspect of astronomy, of figuring out what the universe has given us, has produced, is, I think, and arguably a very important part of what we do. It also happens to be something that I really like, and so I am going to talk about that a little bit. And so I would rephrase Lord Rutherford's statement as this, that astronomy is both physics and stamp collecting. We're going out there and collecting our stamps. We're building new machinery to collect the stamps in a different kind of way. But then we want to use our knowledge of physics to figure out why the universe has made this particular set of stamps and not a different set. How the things that we see around us have gotten to be the way they are. And finally, we need to use our stamp collecting skills in order to make sure that we're not fooling ourselves about what we see in the universe. That, for example, all the brightest stars in the universe are a particular kind of star. Well, maybe that's because we didn't carefully figure out what kinds of stars we could detect with our instruments. And so that idea that we need to organize our data and understand our systematics is one way in which astronomy has ties to lots of other sciences that are also observational. And it's an important aspect. So I would argue that astronomy is both physics and stamp collecting, and both of those things are important. So there are a lot of things we can study in astronomy. There are stars and planets and gas clouds and comets and galaxies. Galaxies are what I am particularly interested in, and I titled this talk, The Beautiful Science of Nearby Galaxies, because of course galaxies are some of the most beautiful things that you can look at. I'm going to now give a brief introduction to what is a galaxy for those of you who had your last astronomy course a long time ago. Astronomers, brief nap. Everybody else, stay with me. So what is a galaxy? Well, this is our own galaxy here on the left. This is the Milky Way galaxy seen over one of the telescopes of the Very Large Telescope on Mount Paranal in Chile. And so those of us in the room who speak Greek know that galaxy is related to the Greek word for milk, and it's named because of this milky appearance across the sky of all of these stars. But when you think galaxy, unless you live somewhere dark, this probably isn't the first thing that you think of. Probably you think of a picture something like this. This is an artist's conception picture of our own Milky Way galaxy. We don't have a picture of the Milky Way. We don't have any way to get outside it and take a picture. So it's a spiral galaxy with these beautiful spiral arms. There are several arms, and they have names. In our galaxy, they're named after the constellations where we find them. We live here, so offset from the center of the galaxy, maybe halfway along the length of the disk. The galaxy seems to have a sort of barred structure in the middle. The arms get further apart as you go further out. And that's the general picture of a large spiral galaxy like the one that we live in. Why does it look so different from Chile? Well, it's not just that things are strange in Chile. It's that a lot of what you see in this picture, although you can see a lot of the stars in the galaxy, you're also looking through a lot of dust. And so it's quite hard to figure out the overall structure of our own galaxy just because we're stuck within it. And in fact, a lot of what people figure out about the structure of galaxies is done by looking at other galaxies where we get the whole view. In our own galaxy, we get a very good close-up view of things close to us, of nearby stars, and of details that we can't see elsewhere. But by looking at nearby galaxies, we can kind of also get the big picture. So here are some more beautiful pictures of galaxies, just to show that there are lots of different types of galaxies as well. So these are all pictures taken with the Canada-France-Hawaii telescope on Mauna Kea. And here we can see a couple more beautiful spiral galaxies. And these two are seen nearly face-on, so we're looking down on the disk. You can see some of these other blobs in here. This is a smaller dwarf galaxy that lives nearby these guys. These are other further background galaxies. This is another dwarf galaxy that lives near our own galaxy, and you can see it doesn't have those nice regular spiral arms. It has some gas and dust in it. That's this fuzzy red stuff here. Here's some of the dust. And then this is a large elliptical galaxy. Again, no spiral arms, and instead of regular rotation, what these kinds of galaxies have is basically kind of chaotic rotation of their stars. They go every which way. They tend to be kind of ellipsoidal shaped. They're not flattened like a spiral would be. And you can see that this galaxy has a lot of other galaxies around it. And in fact, galaxies like this elliptical galaxy, are more often found in galaxy clusters, in neighborhoods where there are a lot of other galaxies. You can see that some of these guys, here's a neighbor galaxy of this guy. This one is closer to being edge-on. And here are some more neighbor galaxies here. And one of the things that it's important to understand about galaxies compared to, say, stars or planets is that they're comparably close together in the sky and in space. So these two are particularly close together. That's a little bit unusual. But the example that we like to give to our first-year astronomy students is that if you take the sun and you say that model the sun as being something the size of a grapefruit, the nearest star is another grapefruit in Calgary. Whereas if a galaxy, you model it as something as the size of a dinner plate and you put it on the table here, the next nearby galaxy might be on a table over here on the other side of the room. So galaxies are very close together compared to their size, unlike stars, unlike planets in our own solar system, for example. What does that mean? It means that galaxies can be shaped by each other. Because they're relatively close to each other, they can and do interact, and that interaction can change their histories. It can actually, we think, turn them into different kinds of galaxies over billions of years. So there's some nearby galaxies, and they're beautiful, and we think they're really nice to look at, and we think we can learn a lot about galaxies from looking at them. But people who study galaxies don't all look at these sort of flashy nearby things. They often also like to work on these nondescript galaxies. And in fact, almost everything in both of these two pictures, aside from a few things which are stars that are in the foreground in our own galaxy, almost everything in this picture is a galaxy. And if you come up close to the screen, you can see some of them look like they've got little spiral arms, but others of them are just little blobby things. And so these are very distant galaxies, many, and we're seeing them as they were in the distant past. So while geologists have rock layers and they can find older rocks on the Earth, we can't find older galaxies nearby, but we can find older galaxies or younger galaxies, depending on how you want to look at it, by looking further out in space, because it takes light a finite amount of time to get to us. And so if we look at very distant galaxies, we can see them as they were in the past. And for example, one of the things that you can learn by looking at that is the fact that there are more sort of blobby galaxies. There are not as many of the nice spiral galaxies if you look further out into the past. And we take that as an indication that interactions between galaxies and mergers were more common in the past. So people use these kinds of data where you pick the most boring piece of sky you can imagine, where there's nothing interesting going on. No foreground stars, no flashy, shiny galaxies here, but just a bunch of stuff. And you stare at it for a very long time with a telescope, and by a very long time I mean maybe a week or something like that, and you can detect a lot of these very faint galaxies. And by detecting a lot of these things, you can do the kind of statistical analyses that let you know how galaxies have changed over time. So looking at these very distant galaxies is great for that. What, of course, you don't get with a very distant galaxy is the detail. These are little tiny blobs, and you can't make them any bigger. You can't magnify them with a bigger telescope, essentially. And so while you can get a global picture of what a galaxy is doing, you can't get the kind of inner detail. You can't see where the spiral arms are, or how the center is a different color than the outskirts, or where the dusty parts are. You can't see any of that kind of detail if you look at a distant galaxy. You can see that kind of detail when you look at our own Milky Way. There you've got all the detail you want, but it's harder to get the big picture. And so the reason that I am so excited about nearby galaxies is that I think they make the nicest compromise between getting the big picture and getting the kind of fine detail that you really want to know what the physics is going on inside them. Okay, so we like galaxies. We want to study galaxies. We think nearby galaxies are great. How do we go about doing that? Well, you know that we use telescopes, of course. And what do? We rely on a couple of basic pieces of physics. The idea that if you're looking at a hot object, it emits different color distribution of light than a cold object. That particular elements have spectral emission lines, which allow us to figure out what a distant object contains. And we observe these things through big telescopes, and we plunk a very big digital camera on the back of them. So this is the MegaCam camera at the Canada-France-Hawaii telescope. And these are real people, not photoshopped, actual size. And so this is a digital camera that's about yay big across. You can't put it, but it's the same technology as the one in your pocket in your cell phone, except that it's a lot more expensive. And these things this is a 340 megapixel digital camera. So what we're doing with the kind of data that we take, we are taking images with these very fancy digital cameras, and you need different kinds of digital cameras depending on the wavelengths of light that you're looking at. We take spectra by passing the light through some complicated device that splits it up into separate wavelengths, and then we put that spectrum on one of these digital cameras. And what we spend a lot of our lives doing, and the students in the room spend all of their time doing, is trying to go from the raw output of these fancy digital devices and turn that into science. So although we like these beautiful color pictures, we spend very little time with the beautiful color pictures. We spend all our time with black and white pictures that have funny looking artifacts in them, and we're trying to figure out how to very carefully calibrate that imagery that we take into precise measurements of exactly how much light is coming from a given galaxy at a specific position at a specific wavelength. So I don't just want to know that this part of the galaxy is redder than that part. I want to know that it's 30.785% redder. I don't want to know that there's some kind of red light coming from the galaxy. I want to know that there's red light at some particular wavelength, which tells me what's going on. And so there's no photoshopping in astronomy. That's where what we spend all our time doing is trying to figure out the best way to take that digital data and turn it into physics. So let's talk a little bit about what's in a galaxy. And you kind of already know this from some of the pictures I've shown, but I want to emphasize it a little bit more. Here's our own galaxy again, lots of stars in it, and stars are a major constituent of galaxies. Galaxies also come with star clusters, which are, you can think of them as almost like little satellites. They are found around galaxies. They're associated with galaxies, but they're gravitationally bound. Mostly the stars are bound to each other and not to the galaxy. And I'm going to talk a lot more about star clusters because I think they're pretty cool. One of the great things about star clusters is that, to first order, the stars in a star cluster are very similar in that we think they have essentially the same composition and the same age, and we think that they were probably all born in the same place, in that star cluster. And so if we want to look at the history of a galaxy, well, it would be great to look at the individual stars in a galaxy, but you can't always do that because once your galaxy gets far away, you can't see the individual stars very well. You can, however, see these star clusters out to much greater distances. And so they serve as kind of probes. They're kind of the tips of the mountaintops that let us look at what's going on inside a galaxy, what its history was. So galaxies have stars, they have star clusters, they also have dust, and that, of course, this is dust in our own Milky Way galaxy here. This funny looking picture is an infrared picture, and I'll get to that again in a moment, but it shows dust in a galaxy which is often called the sombrero. And so this red light here, this is not a visible light image, but this is an infrared light image. This red light is showing the dust basically glowing in a disk around this galaxy. If you look carefully, you can see a bunch of little dots around this guy as well. Those little dots are actually star clusters like this guy here, just much reduced. We find other things in galaxies as well. We find hot gas and cold gas and sort of medium lukewarm gas. And that gas we can see at different wavelengths of light. For example, in this galaxy, which is called Centaurus A, the orange stuff here is very cold gas, whereas the blue stuff here is quite hot gas. And you can see there's something interesting going on with this galaxy in that the cold gas seems to be sort of contained within the hot gas that's spreading out from the center of this galaxy. What we think is going on in this particular galaxy is that it's the remnant of a merger between two galaxies, an elliptical galaxy like this guy here, and a spiral galaxy like this one here. And so this is the remnant of the spiral galaxy. It's got the dust. This stuff here is the remnant of the elliptical galaxy. And the excitement of the collision has made the black hole in the center of this galaxy get very excited and start shooting out these jets, which involve both cold and hot gas in various places. Galaxies also have dark matter. You've probably heard that phrase. I'm not going to talk very much about dark matter today. It's just not a topic that I happen to work very much on. Plus, it doesn't make very nice pictures. And so, you know, we're all about the nice pictures here. So I mentioned different wavelengths of light and how we can study galaxies in different wavelengths of light. And so here's an example that shows you a little bit more about what's going on. So this is a famous galaxy known as the Cartwheel. You can see why. And this is a color composite made up of a bunch of different wavelengths of light, where these are showing the individual pieces that went into that composite. And so we have X-ray light here from the Chandra Observatory. And you can see that this picture looks quite a bit different from these other pictures here. The X-ray light comes from very hot things in the galaxy, and you can see there's some very hot gas in the center, but also some very hot objects around the outside of the wheel. Not so much, there's a little bit in the center, but not so much. Ultraviolet light is coming from mostly places where there are new stars in the galaxy, and you can see there's a lot of new stars again around the outside. The visible light shows you more light from these things. These are sort of the cores of the original galaxies, and so you're seeing more of the old stars in that light. And then finally we have infrared light, which is showing you the oldest stars and also where the dust is in these galaxies. And so by looking at these different wavelengths of light, we were able to get different pictures of what's going on in a galaxy. And it used to be very much so that people were radio astronomers, or they were X-ray astronomers, or infrared astronomers, and they would work on one wavelength of light and use that as kind of their hammer to try to study any particular object. And so I worked on an infrared telescope. I had an infrared hammer, and I used it to hit a lot of things. But these days, I think it's less common for people to specialize in one wavelength, and more common to try to bring the science questions to the tools rather than the tools to the science questions. Okay, so questions. This young man has questions. He wants to know what are the big questions in extragalactic astronomy. Well, the big questions are, how did galaxies get here? How did they form their stars? When did they form their stars? Were they always in the shapes that we see them now, or were those shapes different in the past? How did the chemical elements that are found in galaxies, so the carbon and the hydrogen and the oxygen, not the hydrogen, the carbon and the oxygen and the nitrogen, the elements that we're made up of that we like very much, where did those come from? We know that they came from stars, but when were they formed? Did they come from stars that are in the galaxy now? Did they come from outside the galaxy? And we think that all of these questions of when galaxies formed their stars and how they came together have to do with where galaxies are found. And so you'd like to know, how is that changed with time? How is the clustering together of galaxies changed with time? And how does that clustering affect what happens to galaxies? So, I mean, the big picture thing of what we're trying to figure out when we study galaxies is really, how did we get here? We live in a galaxy, and we're pretty sure that most planets that we're going to find are going to be found in galaxies. And so we want to know, how did things arrange themselves so that we find ourselves here today, thinking about this and wondering when the reception is going to start. So how did I get into this game? That's kind of my next topic. And Shantanu mentioned my PhD supervisor, who is pictured here. And this is something that we are lucky to have in astronomy. We have a wonderful database of basically every paper that's ever been published in astronomy. And you can use that and put it together to find someone's author network and see how they're connected to all the people that they have written papers with. And the reason that I wanted to show John's and not to show mine is that mine is not as interesting, but it also, he has these interesting little sets of clumps. He was someone who worked on a lot of different areas in extragalactic astronomy, from X-ray clusters to galaxy redshift surveys. You can see he was a member of a big team that wrote a lot of papers together. And he also worked on star clusters with me, which is why I'm way up here in the corner. And so when I started my PhD, I actually did a first project with John in which I worked on galaxy clusters, and so I would have ended up over there. And then I decided that star clusters were more fun, and that's what I ended up working on instead. And I show this picture not only to explain how I got here and got into this game, but to encourage those of you who have some mentor out there that you haven't seen in a while to say thank you to them if they helped you get where you are today, because sometimes our mentors leave us in a hurry and we don't get a chance to say that. So I worked on extragalactic star clusters for my thesis, and this is a galaxy we'll be seeing more and more of in this talk. It's the Andromeda galaxy, the nearest big galaxy to our own. And my thesis was on the star clusters that were found in this galaxy. So this is an example of one of those. It's one of the biggest and brightest ones. It's not visible in this picture. It would be one of these tiny little dots, except it's way over here. It's not quite on the picture. So the thing that I spent my thesis doing was staring at a lot of pictures that looked like this and trying to decide which of them were star clusters and which of them were background galaxies and which of them were just blobs. And the fact that I managed to rope my PhD advisor into also staring at them with me is one of my prouder achievements, actually. So a few of these turned out to be real star clusters, and we now have them listed in the catalogs of star clusters as BH07, Barmby Huckra 07, which is also kind of nice. So again, we're stamp collecting here, but what is the point of the stamp collecting? Again, we want to know how galaxies form their stars, and one of the ways they form their stars is by making them in clusters. And interestingly, the Andromeda galaxy, although it's about the size of our own Milky Way, has at least 3 times as many star clusters. That's something we still don't understand. It turns out to be handy for people who like to study star clusters. There's more of them. And it lets us probe a little bit more deeply into the history of the galaxy. We can slice and dice those clusters a little bit more. So that was my PhD thesis, and as Shantanu said, I moved across the street after I finished my PhD to work for this gentleman. This is Giovanni Fazio, who was the PI of one of the instruments on the Spitzer Space Telescope. This is Mr. Spitzer here. He had nothing to do with the telescope. His big contribution was that he was one of the 2 people who really got the Hubble Space Telescope funded and operating. And so NASA typically doesn't name missions after people unless they're dead. He wasn't dead when the Hubble Space Telescope got launched, but he was dead by the time the Spitzer Space Telescope got launched. And in fact, the name was, they had a contest to rename it. It had some NASA acronym name before launch. And the person who suggested Spitzer was actually someone from Yukon, which I thought was pretty interesting. So this is the instrument here. It's this black thing, which I never got near because as a Canadian, I was judged to be a security risk. So I was on the other side of the continent analyzing the data, and a lot of my time was spent looking at pictures like this, going, what is this white streak, and what are these black dots, and how are we going to get rid of them, and why do the stars look triangular, and all that kind of messy, systematic stuff that you have to do in order to get science out of an instrument. Is stuff that you have to do first. So we did get all the messy the messy systematic stuff sorted out. And eventually one of the things that we were able to do with Spitzer was to use it to map the entire Andromeda galaxy. Something that nobody had ever been able to do before because the available detectors, the available cameras that worked in the infrared were very small compared to the size of the galaxy, and it took forever to get them to register enough signal to make a decent map. But Spitzer had much better technology, you could do things much better, and what we finally got was a picture that looks like this. So this is the same galaxy as a couple of slides ago, but now seen in the infrared instead of in the visible light that you might be more used to seeing galaxies in. This galaxy also, we're not seeing it face on the same way as some of the other spiral galaxies that you're used to. We're seeing it at an angle, and so that's why it looks kind of lopsided here. You also will notice if you own a Mac, you might recognize this galaxy. It's the same one that Apple puts on your Mac picture. Apple doesn't like this satellite galaxy. They actually cut this one out. And I don't know why that is, but next time you look at your Mac, have a look and see that it's not there. So this is a satellite galaxy up here. This is another satellite galaxy down here. This red stuff, again, is all dust in the Andromeda galaxy. Most of the dots we see here are actually stars in our own galaxy that are just projected in front of Andromeda. But the blue fuzz that you can see here, that's the old stars in Andromeda itself. So, okay, here's the blue fuzz all by itself, just so that you can get a better picture. And one of the ways that the Spitzer telescope really revolutionized studying nearby galaxies is the fact that you could see the infrared light which comes from old stars. Why are old stars good? Well, because young stars tend to be more massive. When you look at the old stars, you're looking at basically most of the mass of a galaxy. And so you can use a picture like this to estimate the total mass of Andromeda, which we did. And we learned that using the word trillion is a good way to get your PR people to make a press release. They love that. And so we were able to estimate the mass of Andromeda and use the word trillion in a press release. That was pretty neat. And you also notice that one of the things that's interesting here is that you don't see the dust. You don't see any of those dark lanes. And that's because the infrared light penetrates through the dust. And so if you really want to know, sort of see the backbone of a galaxy, infrared light is a good way to do that. Now here's all the dust in its glory without all those pesky stars. And you see the galaxy looks much more complicated. It's got lots of sort of spurs and spirally bits. It's got spiral arms. It's kind of a mess. This region here is sometimes called the Ring of Fire for obvious reasons. One of the things that you can do with a picture like this is try to estimate the rate at which new stars are forming. How can you do that? Well, it turns out that what lights up this dust in Andromeda is basically the ultraviolet radiation from young stars. And so by counting the amount of light that's coming from dust, it's another way to estimate how many new stars are forming in this galaxy. And so what you find in the strange units that astronomers use is that Andromeda is forming new stars at the rate of 0.4 solar masses per year. So every year it's turning an amount of gas into stars that's about 40% the mass of the sun. Of course, real star formation takes much longer than a year. That's just the funny units that we use. But this number was kind of odd because the Milky Way has a star formation rate that people typically quote as being about 1 solar mass per year. And so Andromeda, which actually looks like more exciting things are going on, seems to be much more boring in terms of how fast it's forming stars, which is something we still don't quite understand. So I worked with a colleague who also looked at this picture and wasn't excited about the outer dust ring here. This is the same picture as before, just in a different color scheme. But notice that in fact, if you squint hard enough, you can see that there seems to be some kind of inner ring in the middle of the galaxy as well. And not only is there an inner ring, but the inner ring is not centered at quite the same place as the outer ring. And his idea was that, in fact, the reason that Andromeda looks so kind of messy and weird is that one of its little satellite galaxies actually passed through the disk of the galaxy about 200 million years ago. And one of our colleagues had a partner who was a good cartoonist and noted that if the dinosaurs had telescopes, they might have seen this collision at that time. They obviously didn't know the difference between spirals and ellipticals because we think that the galaxy that did the colliding was this little guy, which is an elliptical galaxy. But, you know, maybe their telescopes weren't very good. So that's the Andromeda galaxy as seen in the infrared, and that's one of the big projects that I did while I was working with the Spitzer team. But, you know, you have an infrared hammer, and so you go about and you use it to hit things. And one of the other things that we hit were some of the star clusters that belong to our own galaxy. So star clusters have lots of stars in them, and near the ends of their lives, those stars lose mass. They blow off some of their outer envelopes into space. And we thought that some of these star clusters should have some of that stuff that had been blown off and would be carrying it around. They have lots of gravity. They should be able to keep the gas and dust around. And so we went and we looked at some of the star clusters with Spitzer. This is a different infrared wavelength than the IRAC camera. And, there are the star clusters. Okay, very good. And then we look at them at the wavelength of light where we expected to see the dust. What do we see? Nothing. And so that was kind of a surprise in that we expected that there would be this infrared emission from dust, which we did not find. It turns out that if you talk to the right people, they can come up with any number of models for how to get rid of this dust and why it shouldn't be there in the first place. Of course, they don't want to talk to you before you have your data. They just tell you that afterwards. But I want to point this out as another example of how the kind of stamp collecting that we sometimes do in astronomy, we have a new instrument, we're going to go observe everything we can think of, is important. You can't always go back, as in a physics lab, and run one more experiment. For example, the Spitzer telescope is not taking any more data at these wavelengths. And if we hadn't taken this data, nobody else would have. And we wouldn't know how much dust there was or wasn't in these star clusters. Also looking at things in the Milky Way galaxy, we have hidden in this mess here is the prototype variable star that people spend a lot of time worrying about. It's a star called Delta Cephei, which is one of the brighter stars in the sky. It's a variable star of a type that astronomers use to measure distances. And something that we discovered when we looked at it with Spitzer was that in fact it has all this stuff in it around it. And what we think this stuff is that this blue emission is a wind being blown off the star. And then this red stuff is gas and dust in the Milky Way, and the star is kind of plowing through this dust. It's going from this way over that way and making this kind of bow shock. And again, these stars were not known to lose mass before we looked at them. It was thought that they might because there was a problem with measuring masses in a couple of different ways. And once we looked at a sample of them, we were able to say that some of them were losing mass. So, stamp collecting and looking at interesting things. What else can we do with an infrared telescope or a visible light telescope or an X-ray telescope? Well, we can look at some more star clusters. And that's a lot more of what I've been doing, particularly since I got here. So, star clusters, because they have a lot of stars in a very small area, those stars sometimes run into each other. That doesn't normally happen in galaxies, but it can happen in star clusters. And when those stars run into each other, processes can happen that lead them to emit X-ray light. And so what I've been working on with some students and colleagues here is finding the star clusters, for example, in this galaxy M51, that emit X-ray light, trying to find out how they are different from the ones that don't emit X-ray light. Again, this is star clusters in the Andromeda galaxy, finding the ones that emit X-ray light, they're the red ones, and seeing that they're different from the white ones that don't emit X-ray light. But if we just look at star clusters in galaxies as a whole, and that's what this plot up here shows you, they turn out to be actually quite similar between different galaxies, which is something we don't quite understand yet. I've also spent a lot of time since I got here working on the Andromeda galaxy and other aspects. And so looking at the regions in the Andromeda galaxy that are forming new stars, that's what most of these guys are here, trying to measure their brightness at different wavelengths and understand their content of heavy elements like carbon and nitrogen and oxygen that I measured before. I put in this plot just for our Astronomy and Physics 9028 students. It's not actually the galaxy, but it's a chi-squared surface. And so we're trying to fit a couple of parameters where we're trying to understand how the galaxy element abundances change as a function of distance from the center. And it just happens to look exactly like the map of the galaxy on the sky. Isn't that cool? And then finally, I've also done a little bit of work on other kinds of galaxies, not the big flashy galaxies, but the little kind of wimpy galaxies. This is Leo 1. This is called a dwarf spheroidal galaxy, and this is the galaxy here, this sort of overdensity of blue stars. What we're trying to do with this galaxy is find the red ones in here. Again, those are the dusty mass-losing ones. This galaxy over here, NGC 1569, is a dwarf galaxy, not like this one, which is just old stars. This one has tons and tons of new stars, and that's what all this messy stuff around here is showing you. And what we're trying to understand with this galaxy is how that formation of new stars is affected by what's going on both inside and outside the galaxy. So, lots to do with nearby galaxies. Lots of galaxies to look at, lots of ways to look at them. Where is this field going to go in the future? Well, I think there are a couple of big things that are going to happen in the future. One is something that I've gotten very interested in, which is the concept of astroinformatics. The idea that we have all this big data about these galaxies. We have gigantic multi-gigabyte images. We have huge databases. We have lots of wavelengths. We have lots of catalogs. And we're not very good at putting all of that information together. We need more than text files on our hard drives to cross-reference this stuff, and that's almost the level that we're at. And a lot of what I'm doing in my current research is trying to figure out what tools are out there that we can apply to better understand what's going on in galaxies. The other thing that I think is important for the future is the new facilities that we're going to have. One of them is the James Webb Space Telescope, which is this crazy looking thing here. It is not yet in space. It is still being put together. It's NASA's successor to the Hubble Space Telescope, but it's much bigger. And to give you an idea, these star shades, this sort of sunshade thing that folds out, this is about the size of a tennis court. So this business is going to launch kind of all folded and crinkled up, and then it's going to unfold, and it's all going to work, they tell us. And it's going to take fantastic data. This thing is about 3 times the diameter of the Hubble. It's going to work at infrared wavelengths. It's going to be fantastic. It's going to let us see much deeper, and it's going to be wonderful. The other telescope not yet built is this thing here, the 30-meter telescope. So this is a project that Canada is involved with, along with a number of other countries, and it's just what it says, it's a 30-meter telescope, where 30 meters is the diameter of the mirror. To give you an idea, a big telescope these days is 10 meters, and the telescope sensitivity for some things goes as the square of the area, and for some other things goes as the 4th power of the area. So you get a lot more if you go from 10 meters to 30 meters. And if we can really get the money to build this thing and make it work, it's going to, again, allow us to make pictures of Andromeda that look like pictures of our backyard in space. It's going to let us see lots more detail, lots more faint things, and ask new questions that we haven't even thought of. So I want to close by saying thank you to everyone in this picture here, most of whom are in the room, and a lot of these other folks are in the room as well. And to all of you for staying awake extremely well at the end of a busy week. So thank you so much.
Thank you very much, Pauline, for beautiful results and a very clear delivery. Let's open up. We have plenty of time for questions.
Is there any way of knowing what M32 looked like before it plowed through Andromeda?
Is there a way of knowing what M32 looked like before it went through Andromeda? So people have tried to model the collision, but of course, what you get out of these models is often what you put in. People certainly have tried to look in detail at the structure of the galaxy and see whether it looks like a regular galaxy or a galaxy that's had kind of its outer parts torn off. But the problem is, because M32, and I'll just remind people, M32 is this little satellite galaxy here, because it's kind of projected onto M31, it's very hard to figure out to separate it from the background galaxy. So people try, but it's a little chancy.
I was wondering how you define dust in terms of composition and size.
How I personally define dust?
How astronomers define dust.
Right. So yeah, our definition of dust is like not the dust bunnies under your desk kind of thing. I think it depends on who you ask, but you're talking about things which are, I'm going to get this wrong, and then Jan's going to laugh at me. You're talking about things which are sort of thousands of molecules to maybe a few microns in size. I mean, there's a range of sizes, right? But you're talking about relatively small things for the most part.
Pauline, you talked a little bit about it in bits of the slides, but not too much. What is there? Are there challenges to overcome with regards instrumentation and detection? I don't know, detection limits, or you showed some gaps in some of the. So how do you overcome those? And in particular, I wondered whether do you use different instruments to help overcome missing parts of data that's obtained from one instrument? So can you somehow mesh data streams and use one to infer in the other?
So to do the second part of your question first, yes, that is certainly done, particularly at some wavelengths. At radio wavelengths, for example, people will make kind of an equivalent of a very big telescope by putting lots of small telescopes over a large area. And that gives you the spatial resolution, the detail of having one big telescope with the same large area. But what it doesn't give you is the collecting area, the ability to see the faintest fluxes. And people will put data together from a bunch of little telescopes and one big telescope in that way. It's less common at other wavelengths, sometimes because the things that we're looking at are varying in time, and so you can't coordinate to get the same telescope to look at different things at the same time. Instrumentation is always a challenge, and I think astronomy, more than many other fields, is driven by how well our instrumentation works. How can we figure out how to make a more efficient detector or a better telescope? And in some wavelengths, that technology is driven by other areas. For example, infrared arrays were first developed for the US military, and that's why I wasn't allowed to go anywhere near the infrared arrays. But there are other wavelengths of light where there's no obvious military or commercial application, and so often it is the astronomers that are pushing the boundaries of the technology.
For the instruments that are land-based, are there particular areas of the world that are ideal for the positioning? And then my second part would be, then when you have something that is presumably moving about, are you able to stop it, or do you ever want to stop it? So the difference sort of between being stationary and ideally located, and then being able to move about, and where do you want it to go?
Right. So the places that we like to build telescopes on the Earth are places where the airflow is very smooth. And so what you typically want is a big mountain near the ocean. And so Hawaii, Chile, the Canary Islands are all good locations. You also want to think about the weather, of course. Yeah, it's tough. It's a tough life. You want to think about the weather. It doesn't matter if the airflow is good if it's always raining. And you also want your telescope to be somewhere where you can see more of the sky. So a telescope on the equator can see the whole sky. A telescope on the North Pole can only see the northern half of the sky. So do you ever want to move them around? That's not very common. The telescopes that move around, there are a few that people put on balloons and they go on circumpolar flights. And sometimes they crash, and so that's why people don't like that so much. There's one telescope that lives in the back of a 747, and they fly it around. And that's a very interesting telescope that's had a very long and strange history. But typically they're such big behemoths that the telescopes themselves don't move. Sometimes the instruments will move from telescope to telescope. So you'll take a camera from somewhere and take it somewhere else. But telescopes in general, once they're there, they're there.
Well, where is this one meant to be built if it gets built?
This TMT, it would be built on Mauna Kea, so on the Big Island of Hawaii, just below the summit. And in fact, they have started. They don't have all the money for it yet, but they've started building this piece of the road just recently, I'm told. So, you know, we got no telescope. We got a flat place on the mountain. Yeah.
Peter, can you say a bit more about what special tricks you use, or how hard it is to discriminate globular clusters in the Andromeda Galaxy from foreground stars?
So, okay, so this is a technical astronomy question. Good, I like it. Basically, you sit there and you squint at the Hubble image. You wait for the astronauts to go up and put in a better camera so you can get an image with better spatial resolution. So you're looking for something that's sort of blobby around the edges as opposed to sharp in the middle. And ultimately, what we end up doing with a lot of star cluster candidates is we take a spectrum of them and we measure the velocity. So we see whether the thing is more likely to be a star in our own galaxy, in which case it would have a fairly low velocity, or a cluster belonging to that galaxy, in which case it would be moving usually with that galaxy.
The picture of M31 with M32, there's a thing that was annotated, a hole in the ring. Is that sort of a predicted place where M32 would have come?
That was the idea, yeah. Let me see if I can.
Right. The hole in the ring.
Yeah, so the idea is that this galaxy would have sort of come in through the center of the galaxy, kind of made some ripples which made this ring, and then come back out through this hole in the outer ring. That's the idea.
So we'll take one final question.
Yes, please.
Yeah. I just saw that the astronomers have been researching on star clusters and so on. How much of that can be done automated? Can the computers, after being given some sort of limitations, can they do an automatic search and give some pointers that astronomers should look into these things?
That is a great question. And in fact, my pride in being able to get my advisor to look at all these pictures with me was back when I was doing my thesis, you couldn't figure out a very good automated way to, for example, find star clusters. And there's actually been a huge citizen science project where people who got Hubble data on a lot of the Andromeda Galaxy also couldn't figure out a way to do this in an automatic way. But they have faster computers and we have the internet, and so what they did was take a bunch of these tiny pictures like this and serve them out to members of the public who turn out to be just fine. 5 minutes of training and they can figure out what's a cluster and what's not. And so they had 1 million images of these things, which 100,000 people looked at in 2 weeks. And I did not have 100,000 people helping me with this, which would certainly have sped it up.
Pauline, thank you for a fabulous and fun talk. I'd like to ask our Provost and Vice President, Janice Deacon, to award you your prize, congratulate you on behalf of the whole of the Faculty of Science.
Well, in fact, on behalf of the whole university. So it's really my pleasure to be here and to listen to your talk. As an administrator, it truly is just liberating and reminds me why we're all in the business that we're in. And it's fabulous to see colleagues here and graduate students who you mentor and who can be inspired by your work and your truly wonderful presentation today. For those of us not in the area to have any access to the very complicated work that you do, it was wonderful. So really, on behalf of the institution, deepest and proudest congratulations, and we are very proud and honored to have you here as a member of our faculty at Western. Thank you. Thank you.
Congratulations again, Pauline and Janice. Thank you so much for joining us. We know how busy you are. It's a real honor to have you visit the Faculty of Science. And seeing we have another Vice President here, Gita. I think everybody knows Gita, and John Dirksen is also here with us. And Shantanu, you have a treat for us, do you not?
I'd just like to invite everyone to stay and join Pauline and enjoy each other's company in a reception following the atrium.